In this section, we'll finish looking at the structure of proteins by reviewing tertiary and quaternary structure. In this section, we will focus on the tertiary and quaternary structure of proteins. So we'll be looking at how different amino acids can interact through their side chains with each other to form the tertiary structure of proteins, and then how multiple protein units can come together to form the quaternary structure. So let's move on to tertiary structure. So proteins have a very well-defined three-dimensional structure, and this is based on their primary structure and the interactions between the amino acids. Now, tertiary structure looks solely at interactions between the amino acid side chains. And so the amino acid side chains can have lots of different interactions, and they can either have positive or binding interactions, or they can have repulsive interactions. And both positive and repulsive interactions, or attractive and repulsive interactions, play a role in determining the three-dimensional structure of the protein. So, for example, here we can see that if we have two aromatic rings next to each other, we get van der Waals interactions. We can get repulsive interactions between polar hydrophilic groups, such as OH groups, and hydrophobic groups, such as aromatic rings. We can get electrostatic interactions or ionic interactions. We can also get hydrogen bonding, such as with the groups up here. And it really is the amino acid side chains that determine the tertiary structure of the protein. Now, this causes protein to fold up and adopt its shape. It also means that the protein can possess some areas that are hydrophilic and others which are hydrophobic. So typically proteins will have hydrophilic amino acids on their surface, and this enables them to be soluble. So a lot of proteins will either be solubilized in the cytoplasm or in the blood or into intracellular fluid or whatever, but they'll be in an aqueous environment, so they need to be soluble. But the insides of proteins are often hydrophobic, and we can see an example of that here. So the internal cavities of proteins can be hydrophobic, and this is a way for them to exclude water to allow molecules to bind. Now, all of these binding interactions are intramolecular. They are all interactions which occur between the same protein molecule, or between functional groups in the same molecule of protein. And therefore, these are all intramolecular in nature. But if we know what binding interactions or potential binding interactions we have, we can design drug molecules to exploit these interactions and facilitate the binding of a brand new drug molecule to our target protein. Now, just to give you some more examples of interactions that can happen to form tertiary structure. Now, one of the most important is actually formation of a disulfide bond. Now, this occurs when we have two cysteine amino acids in close proximity. So the sulfurs within the cysteine can form a covalent bond called a disulfide bond. And this really does help to determine the structure of the protein. Now, we can also have ionic bonds between oppositely charged amino acid side chains, and these are called ionic. These are ionic in nature, but they're also called salt bridges. So you may see that term in the literature. Now, we can, of course, also get hydrogen bonding between residues that can act as hydrogen bond donor and acceptor, and again, these contribute to the tertiary structure of the protein. Now, finally, we can also get van der Waals interactions between hydrophobic amino acid side chains, and you can see an example of this here. But all of the binding interactions that I told you about when we're looking at intermolecular binding interactions can also happen as intramolecular interactions that help determine the three-dimensional structure of proteins. And so knowledge of these interactions doesn't just apply to how drugs can bind to their target, but also applies to the fundamental basis of how these proteins are formed and why they adopt the shape that they do. So what types of interactions are most important for determining the tertiary structure of proteins? Well, it's not the covalent disulfide bonds and ionic bonds that have the most effect on the structure of the protein. Now, these are actually very limited in number. Only a very small percentage of proteins are made up of cysteines. You might only get 1 or 2 sulfur-sulfur bonds per protein, or perhaps even none at all. Now, it turns out that actually hydrogen bonding and van der Waals interactions are far more important. Now, the hydrophobic or hydrophilic nature of amino acids is very important in an aqueous environment. And as I've already said, this can help the protein to fold up to create a hydrophobic binding pocket. And so if we have a look at the example just here, we can see that this peptide chain is able to form hydrogen bonds with between some amino acids and water. But other amino acids are hydrophobic, and what will actually happen is the protein will fold up so that the hydrophilic amino acid residues are on the outside of the protein, and the hydrophobic side chains are in the center, away from the water. Now, the surface of the protein is hydrophilic to enhance hydrogen bonding with water, and so enable it to solubilize. Now, the internal space will contain the hydrophobic residues, and it may be that these act as reaction centers in enzymatic reactions. Now, planar peptide bonds, of course, still restrict the amount of flexibility that the protein has, and so that indirectly plays a role in determining how proteins fold. And so it's the combination of all of these forces together that enable the protein to fold up into its tertiary structure. And so this involves all of the amino acid side chains and all of their properties that contribute to the formation of the protein structure. So we finally move on to quaternary structure. Now, proteins can actually be made from several subunits which are held together by intermolecular bonding. So this is where 2 protein pieces come together and have an intermolecular bonding interaction to hold them together. So for example, we could have this. So this is 2 identical copies of protein held together by van der Waals interactions. These interactions come about because you have 2 hydrophobic regions in the protein, and so they are able to form van der Waals interactions with each other and exclude water molecules. Now, in quaternary structure, ionic bonding, hydrophobic and van der Waals interactions are usually the most important interactions, although hydrogen bonding can also have a significant role. Now, the formation of a quaternary structure is exactly what happens for this particular protein. So at the moment, we're looking at the secondary structure, which has been highlighted to show the alpha helices and the beta sheets. But if we add the second part of this protein, the second subunit, we can get an image of what the protein actually looks like when it's fully assembled. And so here you can see the addition of the second subunit, and suddenly it looks much more complete. It has much more shape to it than it did before. And this joining together of subunits to create a functional protein is not unusual. You can get proteins that have tens of subunits, each of which comes together to form a particular function. Or it might be that different bits of the proteins have different functions within a particular process. And so quaternary structure is where we get multiple units of protein come together and form intermolecular interactions so that they can function as one mechanical unit. So now that you know what binding interactions determine the three-dimensional structure of proteins, and you know what binding interactions drug molecules can have with their target, we're going to put all of this information together. We're going to look to understand how we can use drug molecules to change the activity of enzymes by exploiting different binding groups within the enzyme. We're going to look at how drugs can bind to receptors and we're going to focus on the concepts of agonists and antagonists in particular. And we're also going to look at drugs which can target other types of proteins. Now, these include transport proteins that can move components in and out of the cell, and also structural proteins that form an integral part of the cell structure.